Welcome dear audience, students and scholars. Here I am Dr. Amjad Ali. In this video we will learn ordinary least square OLS assumption. Dear scholar, OLS is the most common estimation method for linear models, and that's true for a good reason. As long as your model satisfies OLS assumption for a linear regression, you can rest easy knowing that you are getting the best possible estimates. Regression is a powerful analysis that can analyze multiple variables simultaneously to answer complex research questions. However, if you don't satisfy the OLS assumption, you might not be able to trust the results. In this video, we cover the OLS assumption, why they are essential, and help you to determine whether your model satisfies the assumption. Regression analysis is like other influential methodologies. Here our goal is to draw a random sample from a population and use it to estimate the properties of that population. In regression analysis, the coefficient in the regression equation are estimates of the actual population parameters. We want to these coefficient estimates to the best possible estimates. Like many statistical analysis, OLS regression has underlying assumption. When these classical assumptions are for the linear regression are true, OLS can produce best estimates. However, if some of these assumptions are not true, you might need to apply remedial measures or use other estimate method to improve your results. Many of these assumptions describe properties of the error term. Unfortunately, error term is a population value that we never know. Instead, we use the next best thing that is available is residual. Residuals are sample estimates of the error for each observation. So there are few classical OLS assumptions for linear regression. Among them, some are mandatory to produce the best estimates. So let's discuss the detail of these assumptions. The first assumption: OLS should be linear on parameters. While talking about the parameters, we have here y is equal to alpha or a plus b x plus e. So keep in mind, here we have a and b or alpha and beta are here are parameter, so these must be linear while our analysis. This assumption addresses the functional form of the model. In statistics, our regression model is linear when all the terms which we have included in the model are either the constant. See here we have a constant and a slope parameter must be linear. So a regression model linear when all the terms in the models are either constant or a parameter multiplied by an independent variable or linear. So if we have a y is equal to a plus b square x plus e, so this is our non-linear model in case of parameters. So we cannot apply simple regression or OLS on either multiple linear regression on this, because here we have a slope in square root, so that's why we cannot apply OLS. In fact, while defining the characteristic of linear regression in this function form of the parameter rather than the ability to model a curve in a nature, so linear model cannot be a curvature by including non-linear models. We have a curve or polynomial, or we have sometime exponential function. So for the OLS regression analysis, you have to convert these non-linear models or the non-linear relation into linear relation. To satisfy this assumption, then you can apply simple regression or multiple regression, linear regression, by talking about that. So when you have a variable x and y, and when the graphical representation of x and y look like a straight line, so this means that there is a linear relationship between our independent and dependent variable. But if the relationship shows a curve type, or you can say that curvy shape, then we can say that our relationship between independent and dependent variable is non-linear. So first we have to convert this non-linear relation into linear relation, then we can apply OLS. Assumption 2, x values are fixed on a repeated sample. It means that x is assumed to be a non-stochastic. This means that x is a non-random variable. So this may seem arbitrary to you, except in a case where x really is a fixed by an experimental control. But it turns out that this is a pretty much an assumption for convenience in working through the maths. We cannot allow to x be a stochastic, like you imagine that you are drawing a different observation from the same population, and if you can do that experiment repeatedly, then at the end nothing will be changed. You find the same outcome from your selected population or selected sample. Assumption 3, the error term has a population mean of 0. While talking about the error accounts for the variation in the dependent variable that the independent variable do not explain. Random, you can say that random chance could determine the values of the error term for your model to be unbiased. The average value of the error must be equal to 0. So sum of the error is equal to 0. Suppose the average error is plus 1 or minus plus 10 or minus, and this non-zero average value of the error indicate that our model systematically unpredicts the observed values of our selected model. So statisticians refer to a systematic error like this as a bias, and this signifies that that our model is inadequate because it is not correct on average. So you don't worry. But while talking about the solution of this assumption, you don't worry about this assumption when you include the constant in your regression model, because constant forces the mean of the residual to equal to 0. Assumption 4. While talking about the assumption 4, all independent variables are uncorrelated with the error. So like you have x1, x2, so on, x4, 5, 6. These independent variables are not related or are correlated to your estimated error term. So if independent variable is correlated with the error term, we can use the independent variable to predict the error term, which violates the notation that the error term represents the unpredictable random error. We need to find a way to incorporate or correct that information into regression model itself. This assumption is also referred to as an exogeneity. When this type of correlation exists, there is endogeneity. A violation of this assumption can occur because there is a simultaneity between the independent and dependent variable, omitted variable, bias, you can say, or the measurement error in our independent variable. Violating this assumption bias the coefficient estimate. To understand why this bias occur, keep in mind that the error term always explains some of the variability in the dependent variable. However, when an independent variable correlate with the error term, and any independent variable correlate to the error term, OLS is incorrectly explain the variation in the dependent variable. So for the correct estimates of OLS, the independent or explanatory variable have no correlation with the estimated error or with the error term. Assumption 5. While talking about the assumption 5, the errors are uncorrelated with each other. Keep in mind that errors are, when you get the series of the error, the series of the errors are uncorrelated, or errors are independent of each other. Keep in mind that errors are independent of each other. Like there is no relationship between U1 and U2 or any U4 or U5. One observation of the error term should not predict the next observation. For instance, if the error of one observation is positive, and that is systematically increase the probability that the following error is positive or negative. While talking about maybe negative, and that is systematically increases the probability that the following error will correlate to that error. If subsequent error is more likely to have a positive sign or negative sign following your previous error, this is known as a serial correlation, or sometimes we can interpret it as an autocorrelation. Okay, so keep in mind that you have to control that there is no serial correlation or autocorrelation among your estimated or your error series. Sorry. Okay, while talking about the assumption 5, keep in mind that you can draw a graphical presentation of the error with respect to time. If there is any straight line relationship is found between the errors, then we can say that there is a chance of autocorrelation or serial correlation. Let's see. While talking about the linear regression, we say that the relation must be a straight line, but when you are drawing the error term in a graphical presentation, that it must be look like as. If you have an error here and time here, so if the error look like that, then we can say that there is no autocorrelation, and if the error series look like that, we can say that there are chances of the autocorrelation. If you have the information that allow to predict the error for the observation, you need to incorporate that information into the model itself, so that serial correlation most likely occur in time series model. You have to resolve this issue. You might need to add some other explanatory variable in the model that capture that information. So serial correlation reduces the precision part of the OLS estimates. Normally, analysts can also use time series data for the dependent and independent variable relationship. So then there are chances of the autocorrelation or serial correlation. Sixth assumption. While talking about the sixth assumption, the error term has a constant variance. So when the error term has a constant variance, this means that there is no heteroscedasticity. And if the error has a constant variance, then we call it homoscedasticity. The variance of the error should be consistent for all the observation. In other words, the variance does not change for each observation or for a range of observation. This preferred condition is known as homoscedasticity, same variation or same scatterness. If the variation changes, we refer to that as a heteroscedasticity or different variation. So keep in mind that there is homozygosity for the for applying the OLS. The easiest way to check this assumption to create a residual versus a fitted value plot. On this type of graph, you find the heterozygosity appear as a cone shape, like a cone shape, whereas the separate of the residual increases in one direction in the graph, or you can say the spread of the graph will show the homozygosity. And moreover, the heterozygosity also reduces the precision of the estimates of the OLS linear regression models. So keep in mind that while talking about the autocorrelation and homozygosity are both true for the error point of view, when we have these two autocorrelation and homozygosity assumption, we can call it a independent and identical distribution. So and our error is a spherical error. Assumption 7. No independent variable is a perfect linear function of one another or each other. So this means that our explanatory variable has no correlation with one another. So this means that there is no direct correlation among the explanatory variable. If two variables are correlated to each other, this is known as multicollinearity. So there is no multicollinearity among explanatory variable. So keep in mind that OLS cannot distinguish one variable from the other when they are perfectly correlated. If you specify a model that contains independent variable with perfect correlation, your statistical software cannot fit your model, and they will display our error if you have a perfect multicollinearity, and they cannot run your regression, especially when we are talking about e-view. So you must have to remove one of the variable which create a multicollinearity among the selected variable. So keep in mind that you cannot afford multicollinearity for applying OLS. Eighth assumption, OLS 8 assumption. The error is normally distributed. While talking about the error is normally distributed, OLS does not require that the error term follow a normal distribution to produce unbiased estimate with the minimum variance. However, satisfying this assumption allow you to perform statistical hypothesis testing and generate reliable confidence interval and prediction interval as well. If you have an error, and when there is a bell-shaped curve or bell-shaped relationship can be established when you draw that error in a graphical presentation. So this means that your error term is normally distributed. While talking about the error is normally distributed, the easiest way to determine whether the residuals follow a normal distribution is to assess a normal probability plot. You can draw it on a graphical presentation, and you find that either your error term has a issue of non-normality, or your error is normally distributed. Assumption 9. While talking about the assumption 9, number of observations must be greater than number of parameters. While talking about the number of observations must be greater than number of parameters, let's see, here we have a simple linear regression model, y is equal to alpha plus beta x. So see, here we have two parameters, alpha and beta. So for the regression analysis, you have to data at least 3 observations at least, but for the time series analysis you have to more than 20 or 40 observation for for getting the unbiased result. So keep in mind that we cannot run any regression analysis if our parameters are greater than our number of observations. Like if you have a model y is equal to alpha plus beta x1, like beta 2 x2 plus beta 3 x3. So see here, at least you have a 5 observation for this multiple linear regression analysis. So we have to put a error term or residual. Assumption 10. X values are independent variables should not be same. So keep in mind that if you have a series of independent variable, so manage to your data that that the values of independent variables should not be same. If the values of the independent variable are same, then we cannot find any variation or any change with respect to independent variable to dependent variable. So keep in mind that x values or independent variables should not be same value, have not the same value. 11th assumption. Regression model should be correctly specified. While talking about the specified, it means that here is a no specification error. It means that specification that there must be some economic understanding. While talking about the economic understanding, that this your regression model have some theoretical background and some logic behind the selection of these variables. If you are selecting the your variable randomly without following any logic or any theory, then this is called the model specification error. And if you have a model specification error, then you have to face the multicollinearity and some other issues of the violation of the OLS assumption. Okay, why should you care about the classical OLS assumption? Okay, in a nutshell, when we are talking about the care about the classical assumption, in a nutshell, your linear model should produce residual that have a mean of 0, have a constant variance, and are not correlated with themselves or other variable. If these assumptions hold true, the OLS procedure creates the best possible outcome in statistic estimator that produce unbiased estimates that have the smallest variance and refer to being efficient. Efficiency is a statistical concept that compares the quality of estimates calculated by a different procedure while holding the sample size constant. The OLS is most efficient linear regression estimator when assumptions hold true. Another benefit to satisfying these assumptions is that as the sample size increases to infinity, the coefficient estimate converge on the actual population parameters. If your error term follows the normal distribution, you can safely use this regression model for hypothesis testing to determine either your independent variable have entire significant impact on your dependent variable. You can also produce reliable confidence interval and precision interval, or you can make the prediction of on the basis of these estimated results. So keep in mind that knowing you're maximizing the value of your data by using the most efficient methodology to obtain the best possible estimate set of data in your mind. So keep in mind that it's worthwhile checking these OLS assumptions. The best way to assess all of these assumptions, to plot the residual, to learn how to do or what to do with other assumptions of the OLS. So, dear scholar, OLS models are extremely useful and have a wide range of application. When you use them, be careful that all the assumptions of OLS are satisfied while doing an econometric test, so that your efforts don't go waste. These assumptions are extremely important and one cannot just neglect them. Having said that, many times these OLS assumptions will be violated. However, that should not stop you from conducting your econometric test. Rather, when the assumption is violated, apply the correct method to fix, and then run the linear regression model, so that you can get a reliable and unbiased estimates or estimated result. So this is all about the assumption of OLS. See you with another video. Ciao.